hear me?
All right, please go ahead with your presentation.
Okay.
I'm going to stop sharing now.
All right, so hopefully you all can all see and hear me currently. If I can just get a thumbs up on that, all will be good. Can you confirm whether you can hear me? All right. So thank you for the online crew. I think you can hear me. Hopefully the people in the room can also hear me as well, if there are any others in the room.
Yes, we can hear you.
Okay,
please
awesome.
Go ahead.
We have a very short amount of time left. And unfortunately, I have another meeting immediately after. So I will do my best to cover this content in terms of the fundamental. I will also make sure that the content that I'm presenting, even the slides that I don't talk about, you'll have access to after this session is complete. But as was mentioned, I am from IBM Research Africa, and this is the 10-year anniversary of the lab, both, let's say, in both Kenya and Johannesburg, South Africa. And we're excited about that. Hopefully, you'll see a little bit more about the 10-year anniversary celebration later on. Most of the content that I'm speaking about today is from resources that are freely available. Here are a set of textbooks that are available online. You don't have to if you choose not to, you can just access the content directly without having to purchase the text. But as a supporter of scholarship, if you can find an opportunity to support authors, if you can do so. So let's start this conversation by level setting. AI, it's a term that is thrown around a lot, but what does it mean? The working definition that I have come to learn with working with an IBM is AI is the term or the noun that refers to systems that are taught to simulate human intelligence and thought processes. Simulate is very important. It doesn't mean that it's going to replace human intelligence. It doesn't mean that it is better than. It is simulating human intelligence and thought processes for a particular purpose, to assist us to get meaningful work done. AI and artificial intelligence, as the full phrase, because depending on who you talk to, AI could be something else. But at the core, it tries to mimic human functionality, human capabilities. Machine learning is not AI. Machine learning is a subset of AI, where you're mimicking humans by learning from experience. And by experience here, we're really focused on data. In this ML space, much of the emphasis goes on supervised and unsupervised learning. And today we're going to talk about reinforcement learning, which is something else. But the reason why the emphasis has been on supervised and unsupervised learning is that over the past, let's say, 15 years, there have been an unreasonable number of successful demonstrations of the power of machine learning that have come from these two spaces. Much of that is driven by the acceleration of compute, the acceleration of sensing, meaning the ability to generate data in a manner that we have not been able to see or use before, and then in terms of storage. But RL has been around and is now starting to step out of the limelight, which is why I'm really excited that that's the conversation that we're talking about today. In terms of ML, we know about classification, we know about regression, we know about ranking, we know about clustering. Again, all of these are things that we normally see in the supervised or unsupervised space. But what we're trying to say is there are examples of problem domains that can fit within these categories, right? You have a classification task. You'd like to assign a label or a category to all the items in a corpus, right? So once you can frame a problem in that particular way, you now understand how to take a particular set of tools from machine learning and apply it to solve your problem. So you're leveraging classification in the context of the problem that you would like to address. understanding the tools in the toolkit are critical. And that's why it's really important to understand what types of problems have people used or have people solved with the tools that we are learning or that you are learning in this bootcamp specifically. The history of RL is a fun one. Largely, it's coming from an AI community. So it seems kind of weird for me to say this, but these are separate academic communities on the outside here. So this notion of controls, operations, research, if you were studying this content, let's say 50 years ago, you'd be in a very different department from if you were in psychology. However, many of the tools and techniques that we now know as modern RL did come from these different parts of campus. But with that said, you can learn many things by going back to the history and understanding the origin or where did this particular idea come from. So broadly speaking, reinforcement learning is learning from interaction, and it's specifically goal-oriented learning from interaction. Interacting with what? Well, we're going to learn about, we're going to learn from, and we're going to learn while interacting with an environment. In this particular case, the focus is learning what to do. What to do. So you're trying to map situations to actions by learning to maximize a numerical reward signal. So there's an element of, we're not going to focus on how to do it, right? We're just going to say you learn what to do, and you learn what to do by trying to map a situation to a particular action. In supervised learning, we're accustomed with this concept of finding an error. What's the error? The difference between the target output and the actual output that you got. What we're trying to do, minimize error. Really straightforward. Similarly, in unsupervised learning, we're still trying to minimize error. However, we define error a little bit differently, but that's okay. We then think about reinforcement learning, which isn't about minimizing error. It's now changing the paradigm by saying we want to get as much reward as possible. What's reward? We'll see that in a moment, but it comes from the environment that the system is interacting with. All right, so the learner is not explicitly told what actions to take. They do perform a type of trial and error search through the potential actions. And in full RL, full reinforcement learning, you actually have the possibility of having a delayed reward, meaning you may not get the reward that you will ultimately get now. You may have to wait 2 or 3 or 4 or maybe even 400 steps for the reward to be given to you. So then that means that you have the opportunity to sacrifice short-term gains for potentially better long-term gains. This is a difference between the paradigm of supervised and unsupervised machine learning and this reinforcement learning approach. Right? But finally, we really go back to this trial and error thing, because maybe you've learned something, but you can't just keep exploring or keep learning. Many of you have probably heard this. You can't stay in school forever. At some point in time, you need to exploit the information that you have learned and earn something. So the same principle applies in reinforcement learning. You have to balance the things you don't know yet, which you can find through exploration, and you have to be able to maximize the knowledge that you have gained so far. I will skip the last point for now. When we think about an agent in an RL context, we should think of it as complete, meaning everything that the agent is comprised by is within the box. Everything outside of the agent is considered the environment. All right. Moreover, the agent has the ability to perform a particular action at a particular time. So it's temporally situated. We'll talk a little bit more about that in the future, but in this figure, when an agent is performing an action A, we associate that action with T, the time that that action is being performed. When the agent performs that action in the environment, the agent changes the environment or affects the environment, and then the environment provides a state and a reward at a time t+1, meaning the next step. All right, so that's how the agent is able to affect the environment, by performing an action. Now, in the real world, when you perform actions, maybe the output or the outcome of that action is uncertain. And reinforcement learning algorithms can accommodate uncertainty. So you can have environments that are stochastic or uncertainty is present. So if we were to view this as the terminologies that you should know when we're talking about reinforcement learning, this is the chart to commit to memory. You need to understand what a policy is. And a policy tells an agent what to do. The reward, which I said came from the environment, the reward tells what is good. So one, you can figure out that there are many things to do, but a subset of those things are good, and maybe another subset is not so good. Value. What actions or what sequences of actions are good because they will lead to good things. The model is a way to represent. So a model is exactly as the same types of models that we've talked about in the real world. Maybe we build an understanding of the mapping between, if I do a certain action now, this is what I think will happen based on a model that has been learned. To make these models possible, you have to have this concept of a state, meaning what can you observe in the environment, and an action. What could you possibly do in that environment? All right, so these 6 things: a policy, a reward, a value, a model, a state, and an action. But let me put a little asterisk on the model, the 4th one, because sometimes we can actually learn directly from the environment without actually having a model of the environment. And that's called model-free reinforcement learning. So in the interest of time, I will skip this example. But as I mentioned, all of the content that I'm sharing, you can ground yourself in this wonderful book, which is actually a living text by Sutton and Bartow. So we will come back to this if we have time at the end. But it is showing a practical example of reinforcement learning. But this is where I will reconnect with the slides. So we can think of this table as a table with 2 columns. The first is the state, and the second is a value. Maybe we have a way of enumerating all possible states. So we have n states in this table. And as we enumerate the states, somehow an oracle is able to tell us how good is state 1. So we have a value v that, let's say, exists on the positive real numbers. State 1 in this case looks like state 1 and let's say state n-1 or n-1, 2, 3. Forgive the example here. These are the states with the lowest value. Right? So the idea is that we've learned after interacting with an environment that certain states are better than others. Now, as the number of rows in this table gets really large, it becomes difficult to manage this process of learning. So instead of explicitly listing all the possible states, where the number of states can be on the order of 1 million or maybe even 1 billion, maybe we can learn to approximate the mapping between states and values. When we see the term general function approximator, I hope by now you have gotten this notion that, hey, wait a minute, that sounds like a neural network, because we can use neural networks as one really useful way to approximate states or approximate functions. And in this case, we do see that neural networks show up. So what does this mean? This means that a supervised learning technique is actually something that you can see within the context of a reinforcement learning application. Sounds kind of weird, but one of the things that I hope that you get familiar with is that abstraction exists in many places. So we can talk about neural networks as both a supervised learning approach, which is then embedded into a reinforcement learning approach. So if you go to the textbooks, the historical text, some of the notable RL applications that you will see were coming out of the gaming space. So games, let's say 20 years ago, might have been backgammon. But we also, in that time frame, were able to see examples that applied reinforcement learning in elevator control. And I'll show you on the next slide a little bit about that. But inventory management, this is also something where RL was able to show that it was of benefit. And in this particular case, we think about optimizing either where particular items are placed in a warehouse or placed on shelves, so that you can make the whole process of delivering a particular inventory or managing, let's say, that inventory more efficient. Why would you want to do this with reinforcement learning? Because again, the goal is you can, instead of trying to exhaustively map all the possible states, or instead of trying to regress the best solution over time, RL is a different framing that says, I have a sequence of actions that I could potentially take, and I'd like to learn which of these actions add more value. Right. So in the example of elevator dispatching, again, elevators are everywhere. Probably by this time, we have ridden in an elevator that actually was made efficient through the use of reinforcement learning. So in this particular case, we have to focus on states. So what are the potential states in the system? Well, did somebody on floor 1 press the button? How many elevators are currently moving in the elevator shafts in the building? And in what directions are they moving? How many passengers are in each of the cars that is currently moving? And how many passengers are in the hallways waiting to be picked by the elevator? In this particular case, the actions are, for each of the cars, do I stop at the next floor or do I pass the next floor? And then the rewards for this particular paper is -1 for every time step that a person is waiting. So if you have 50 people waiting on a given floor, then you have -50 as the reward. So negative rewards, you can sometimes think of that as a punishment, but the idea is that you'd like to maximize your reward or minimize your punishment, right? So even for a simple case, we're talking on the order of 10 to the 22 states. So this is really a large problem, even for something so simple. All right, so just to repeat again, the learner is not told what actions to take. So the agent is not told, okay, when you have a certain number of people on level 1, you have to pass level 5, 6, level 4, level 5, level 6, and go immediately to those groups of people that are on level 1. The learner, the agent, is providing a type of trial and error search using the environment to give it feedback. And that feedback comes in the form of rewards, which can potentially be delayed. The learner, the agent, needs to be able to both explore the space and also exploit what it knows, because remember, it's supposed to maximize its reward. And then finally, it's considering the whole problem. It's not figuring out how do you get people from the top floor to the bottom floor. It's saying, how do I get reward out of interacting with this entire system? All right, so let me see if I can play this for a second. And while this is playing, if there are any questions that the DSN team thinks really needs to be answered right now, we can take a little moment to answer those, but I would like to leave some time at the end. I think we have about just under 15 minutes, but we will try to get through this all. But I want to show you these things so that you know what's possible. All right, so are there any burning questions, DSN team? Okay, I will take it as a no. So what's on screen here is an example of an agent which has learned to navigate in this three-dimensional space. And this is a really complex system because you're dealing with something that has to deal with simulated physics, also has to deal with multiple joints. And depending on where you step, your reward could be really low because you can fall. Most of these agents get reward for associated with the amount of time that they remain in action or the distance that they cover. So RL can be used in this case because somebody has defined a reward function that makes sense. Now, there's no guarantee that these things will move in the manner that you would expect. So I'll let you think about that one. So a simplification of the reinforcement learning problem is called the bandit formulation or the bandit problem. In this formulation, you don't have a state that you're concerned with. All you care about is actions and the rewards. So you're making your decision assuming that there is no state. So your goal here, when you choose from one of the N actions, is which action will allow me to get the most reward? All right, so let me repeat that. The bandit formulation, there is no state, but it's useful for us to think about this because it helps us build up to the notion of, let's see what we can do if there was a state. So the distribution of the reward depends only on the actions that you take, or let's say the sequence of actions that you take over time, since the action has a subscript T. All right, so here, your goal is always, with the full reinforcement learning process, to maximize the reward you get over time in the long term. So as T goes to infinity. The way that you do this in a bandit formulation is to keep track of this notion, this concept Q. Q allows us to estimate the value of an action. So if you give it an action as a parameter, the Q will say, this is how much that action is worth. And you can estimate that action, that worth, that value, I should say, by looking at how much rewards you have gotten when you've taken that action in the past and how many times you've taken that action in the past. Right? So this is a way to generate an estimate of how good a particular action is. Now, given that information, given this QT, if you were to be greedy, you can say, well, based on what I know now at time T, let me take the action that will get me the most of this estimated value. So I take the arg max of QT, and that will determine how I select what action to take now. All right, let's process that. We have developed an estimate of how good each actions have been in the past. You look at all the rewards that you've gotten when you've taken different actions in the past, and you look at the numbers of times that you've taken those actions in the past, and you use that to generate an estimate of Q. And then based on the information that you've gotten so far, if you wanted to be greedy, meaning you wanted to exploit, you would just say, given the action that I want to take or the action that I'd like to select, I would like that action to be the one that, based on my knowledge so far, gives me the most reward. Now, the challenge with that is you don't know everything. So maybe there's another action that you could have taken that would have been better at this particular time, but because you had never taken all of the actions that you had taken prior to that, you won't know. So there's a balance between exploring and exploiting, and you can't just do one without doing the other. So in terms of efficiencies, there are multiple ways that we can think about how do you calculate. I think I'll be able to still, I'll get to the point that the keynotes that I needed to hit. All right, so here's an opportunity to look at, if we know the current value Q, and we get a reward now, this is a recursive equation that can allow us to update the new value of Q given the reward that we got and our last reward. Sorry, our last Q value. What's nice about this formulation is all we need to keep in memory are two things. One, the reward. Actually, technically, we don't even need to keep that in memory, but we can update the current value of Q with just really nice, simple recursive equation. We don't need to keep all of the rewards that we have seen over time. The form of this equation is one that we should know, and it's familiar from, think of it as a neural network or basic update rule. We have an old estimate of something, and we take the error, the difference between the target and the old estimate, that's our error. We multiply that by a step size, and we use that to determine our new estimate. And this basic structure is what we will see in all of these types of algorithms. So just to make this a little concrete, here's pseudocode for that bandit algorithm. It's really simple. You initialize your Qs, you initialize your Ns. So at the beginning, you haven't seen any action anytime, so you can set those all to 0. Depending on whose textbooks you read, maybe you randomly initialize your Qs. There's some reasons for that. We can talk about that if you have any deeper questions. But it's a simple loop. You select an action either by looking at the best one based on what you know, which is the greedy action, or you select a random action with probability epsilon. That's now the action that you'd like to select. You evaluate that action in your environment and you get the reward. And then you update your count and you update your Q. That's very simple, but it's really powerful. This is all you will need to implement a bandit formulation. All right. So if we were now to talk about the full reinforcement learning problem, we also have this notion of when you're making a decision, when you're taking that action, you have information that you can use. It's the current state. So because of that current state, you pick a particular action and then you get a particular reward, and you also move to a new state. Now, because of that new state, you select a new action. This is at the T+1 epoch. After taking that action at T+1, you get a new reward. And this process iterates. This process keeps going. So all your agent is trying to do is learn the best policy, where the policy is the probability of selecting a given action given the current state. So mathematicians in the room, close your eyes a little bit because the RL universe has abused probabilistic notation, but that's okay. You get the gist of what they're trying to say. What they would like to do is develop a probability over the actions that are available in the environment, conditioned on the states that are present. One thing I'd like to add, we don't always know the future. Well, some might say we never know the future. So in reinforcement learning, the way that they try to encapsulate this concept of the goal is by looking at the future rewards. So we look at the reward, if now is time T, the maximum possible future reward will be all of the rewards that you get from T+1 to capital T time in the future. If you add all of those things up, then you know the goal. Your goal is to get as much of that as possible. And there are some really cool things that people have done with discounting. And for those of you that have done a little bit of statistics or economics, there's this notion of the future value of money. Well, there's a similar construct in the RL formulation. So what we're talking about here is a scalar reward. And while it's not completely possible that you can represent all possible problem formulations using a scalar reward, it has proven to be surprisingly flexible. So there are a wide range of problems that have been addressed using an RL formulation with this notion of a scalar reward. There have been extensions where you can even have multidimensional rewards. And you can, I mean, it's really easy to see how these extensions can work. But I reiterate, the goal here in RL is not to talk about how you want to achieve it, which is what supervised learning does. It just says that the goal is there to say what you want to achieve. So the things that you want to achieve, those things are things that you would get more reward for. All right. Let me quickly jump to, just again, in the interest of time. This is a complete example of pseudocode for Q learning. This is one of the most basic entry elements in RL. Some may say it's tabular Q learning because they choose to represent Q as a table. But as I mentioned before, you can also use a neural network to represent Q. And in that case, now you're talking about, let's say, in most cases, it would be deep Q learning. The concept is you choose an action given the state using your policy. Right? You always have to be able to find an action based on something relevant. And in this case, that thing that's relevant for the full reinforcement learning problem is your current state. So your policy uses the current state to define or to choose the action. Then you actually take that action in the environment and you observe the reward and your new state. You have some kind of update rule. This is what it looks like for the Q learning approach. And based on that update rule, now you have a new Q value. And you just keep looping. Deceptively simple, but this is the basic core of all RL. Your policy determines what actions you choose. Based on your action, you then update what you know about the world. And that update then changes your policy or it refines your policy. All right, so whether it's double Q learning or whether it's something that looks really even hard to see on the screen, you can see these same basic constructs. You select an action based on something called a policy. You update that policy based on the information that you got, not just when you updated one action, but maybe over the course of a trajectory of actions. Because remember, reinforcement learning can have delayed rewards. All right. With that said, let me show just a quick snapshot of some of the really interesting RL results over time. And I'm going in about decades. So in this particular case, it was an interesting finding where an agent was able to learn to navigate a rigid object through a space. So you can view this as, you've heard of robots that have the ability to do surgery. This was the precursor to that. So imagine a robot learning to move a needle or move a rigid object through a space without damaging any vital organs. That rod maneuvering task was first demonstrated in this context. Autonomous helicopters. As a kid, I wanted to fly them, but I knew that they were really hard to fly. But some researchers, Andrew Ng is probably a name that you have heard of. His lab was one of the, from my perspective, did some really cool work showing how you can do some really wild acrobatic tasks with first learning from using reinforcement learning with a simulated helicopter, and then they actually did demonstrate it in hardware. So the Atari, this was something that caught a lot of attention because these were games that many in the community had played as kids. And now there was work done to extend the environments that were being used in reinforcement learning to include these games. So a lot of the state-of-the-art techniques that we have seen in recent days were first piloted, or many of them were tested on this environment. And what's interesting about it is this is completely pixel-based. So your state are directly taken from an image of a screen. Right now, we're going through this wonderful immersion of large language models. But many of these models are being fine-tuned today using reinforcement learning with human feedback. So these are examples, real-world examples, And these are examples that I think should motivate you to understand that, hey, this reinforcement learning is something that I think should be worth studying. So with that, I'll pause here. There are a few more slides, but I will leave those. If you have any questions, feel free to reach out to me on LinkedIn, Twitter, if you're on there, and I'll take any remaining questions. If I'm not able to answer those questions today, DSN team, feel free to collate, and you can just send me those questions on email, and I'll try my best to respond as quickly as possible.
Wow, thank you so much, Dr. Remy. We apologize for starting out late. Yeah, so we had a bit of time extension.